There was just one dude on their team who had like same amount of points as same on that together, and he was just insane.
Yeah.
That one guy was totally carrying.
Yeah. All right. So we just had the CCDC and we're doing very well. We're in 5th place a month ago, and we were in 2nd place and one it was this weekend. So we're way ahead of an awful lot of big name people like Stanford, you know, and Berkeley and stuff. So that's nice. We'll got another invitational coming in a couple weeks, started December, and everybody's welcome. So come and join us if you like. Should be there, December 1. And we just went to a Splunk competition and won that one too. Kaz was here. He's like the number 5th scorer overall, and I was number 3rd, and here's Naomi, who was number 7. So among us, we won, which is pretty nice. So that's good. Anyway, let me just point out the schedule. I guess there's no need to put it all on the board, but this class is nearly over. Today is the 5th lecture. There's one more meeting on December 5th, and that's it for this class. The final stays available after that for all the finals week if you want it. There's a lot of extra credit, so a lot of people get enough points without taking the final, and that's fine. This time of year, there's always a lot of special events. There was a guest speaker this morning, and there's an OWASP event on Friday, and a guest speaker on Tuesday, and another one on Thursday, and so it goes. Many special events this time of year. So check them out if you're interested. And they're all worth extra credit if you want any of that. So let's talk about the DNS security issues of the day, which have undergone quite a significant kind of change since I last taught this class. And it makes me think I may curtail the last lecture in part or all, because it seems to me like DNSSEC has pretty much died. And we'll talk about that. So here we are. We're going to talk about DNS service disruption and security to protect your DNS servers. And let me see if I can encourage this thing to get off the screen. All right. And so if you want to resist denial of service, then the main thing you have to do, of course, is have multiple servers in a cluster. So if one goes down, the others take over. And then it matters how you distribute them. And just get used to this nonsense. All right. So, all right, of course. All right. Pardon me while I struggle with my computer. All right, so if you distribute your servers across the internet, so they have multiple locations physically separated, that is, of course, the best thing to do, because then one power failure or other kind of problem will not take them all down. And that's geographically a large-scale network distributed, or indeed geo-distributed, where they're in different countries. Much more powerful than the old-fashioned model where you just have a bunch of servers in one server room in one building. These days, almost everybody is putting their stuff in the cloud, which makes it very easy to use multiple providers all over the place. In the old days, people actually bought their own hardware and their own backup systems and their own power and cooling, and then they would put it all in one building. This is kind of like building your own car these days, just sort of nuts. All right. So you can have your authoritative DNS servers at a content distribution network or an ISP, not on your premises, and you can purchase acceleration and protection services to prevent it, to protect it from attacks. You can delegate DNS resolution from those servers to your authoritative server, but that means you're still counting on your authoritative server to stay up. There's also direct delegation, where you just have the primary source of your domain be somebody else's server, which is what Cloudflare does, and that's better if you are willing to trust the cloud provider, but you need to trust them anyway, because if your delegating server went down, even though your primary server was still up, nobody could find it. So here's caching acceleration. You send a request, the client sends a request to the DNS server saying, where is it? And it says, go ask this other server, then you go ask that other server. So both of these servers have to be up for you to get a record, but the SOA will, the first SOA server will cache things, so it doesn't send as much traffic to your other one. So it does save you some bandwidth to make it possible to use a cheaper server, but it does mean both servers have to be up, or after the cache expires, people will not be able to see your record anymore. So you can go through a project and set up a domain and run it through Cloudflare, and you'll see how it works. You must make Cloudflare your authoritative DNS server. They have to be the ultimate repository of DNS, because Cloudflare is very different than other DNS servers. They will change the IP addresses of your server at their will without you even knowing what it is. So you no longer know what the IP address of your server is, and that is intentional because they will redirect your traffic wherever in their wisdom they want to send it to handle the load and to resist the attacks. So your IP address will keep changing to different IP addresses inside the Cloudflare network as they choose to balance things around, and they will then fetch the data from your server and forward it to people so nobody even knows your server's IP address, which is much safer for you and usually much faster and better for your customers, but it does require complete trust in Cloudflare, just like all these services do where you have some other person hosting your authoritative DNS server. If they were to go down, your site would be down. That made people a lot more nervous 5 years ago when everybody expected to own their own hardware. These days, I think everybody is pretty much used to the fact of trusting some cloud provider like Amazon and accepting the fact that in the unlikely event that the cloud provider goes down, we'll be down. Amazon went down several years ago for 4 days, and it took down 10 or 15% of the web. And everybody just cheerfully went back on Amazon and didn't worry about it because it was still better and cheaper than they could provide with alternative services. So Anycast is the logical way to do this. Anycast is the strongest defense if you have a geolocated server. You have multiple servers based around the world with the same IP address, and you use BGP to send the data there. This is what Cloudflare does and the root DNS servers. Anybody that is really big can do this. And that means every bit of traffic to your website is distributed around the whole world. And so nobody can take you down unless they can take down all your servers all over the world. So you've got name server delegation here. Here's an example of this. I go to Cloudflare and it tells you to go ask Tom and Coco at Cloudflare to find out where I am. I don't control my own domain servers except through Cloudflare's control panel. But that's how everybody does everything. You go through your control panel to control your cloud server. All right. So you can put these authoritative servers behind those firewalls, and it's protected by those companies that are hosting it. Cloudflare's entire business model relies on dropping all the attacks, so they're very good at it. So I'm pretty safe up there. And all right, there are other ways to do it. You can have slave servers run by acceleration products like UltraDNS. That's another way to do it. So they put authoritative servers in the private access enter of ISP so that the servers of that internet service provider don't even go to your authoritative servers. They have a local copy. There's many ways to do it. They call that DNS Shield. There are many, many ways to do this. Getting fast enough DNS to service all your customers is a big issue. And this is why a lot of people resisted the DNSSEC and the DNS over TCP, because they wanted to keep it over UDP and small to make it fast, to handle the enormous load. Bind is the standard. DJB DNS was intended to be more secure, but it seems to have been abandoned and no longer maintained, but there are many others. And then we get to DNSSEC. DNSSEC was proposed long ago, around the time IPv6 was in the 90s. It was supposed to sign records so you'd be able to trust them. But for most of its existence, it actually didn't stop any real attacks. So nobody cared. It was only the Kaminsky attack in 2008 that actually caused a temporary interest surge in DNSSEC because it actually stops that one attack. And that one attack was pretty bad, but there was a simpler mitigation for that attack, which is randomizing the source IP address, which, although it is a lot weaker defense, in practice seems to be strong enough to lower the risk down to almost nothing. And so there remains no actual benefit to anybody from deploying DNSSEC. And it has pretty much stalled and died, even more than IPv6. IPv6 is another thing we were supposed to deploy 20 years ago, and everybody said, why should I bother? Because IPv4 is still working, and you have some mathematical argument that this is better, but it doesn't really matter in practical terms. And it was very slow to deploy until we really ran out of IPv4 addresses. And that finally forced people to begin adopting it. Now it's up to 20% of the web or so. But no similar catastrophe actually forced everyone to go to DNSSEC. I think the only thing that would have done it is if there had been another attack that it would stop that really started doing a lot of harm, and that did not happen in the last 10 years. So I think what happened is everybody had a brief surge of interest in it around 2009 and turned 2010 and 2011, and then they kind of realized that no attack was coming, and they kind of just dwindled away. So we're going to see the problem with DNSSEC, in my opinion, is it doesn't solve an actual problem most people have. Most people's problem is a lack of confidentiality of the record from the client to the resolver. And DNSSEC does not do anything about that. The only thing it does is protect servers from cache attacks from other servers. And it does it at a very high expense. That is the other huge problem. You can't just deploy it easily. You got to have these signature records on everything. And the ultimate killer is you must have a private key stored on your DNS server. And you have to somehow deliver that to your DNS server. And that was enough of a pain when you owned your own hardware, but now you have to deliver it to your cloud provider, and almost none of the cloud providers offer this service. So it is really difficult to deploy it, and really very little benefit. So it's a high expense and low value, sort of like a college education these days. It's going out of fashion for that reason. So that's the game. You can verify the resource record signature with the server's public key. The private key is on the server, and you have to have a chain of trust. So you'll have your root is self-signed. You can't get any higher than that. The DNS root. Then you have the top-level domain signed by the root, the particular domain signed by the top-level domain, and that chain of trust means you can trust it all the way up. And this is the same kind of chain of trust you find in HTTPS certificates, going back to the certificate authority and often through 2 or 3 intermediate resolvers, each of which is signed by the one above it. So you can verify these one by one and make sure that you trust the top. And they all use public key encryption and similar routines to do it. So you see a detailed chain of trust. You have to start with an A record. Then you say, how do I know that's really the right address? Well, there's a signature. How do I know it's the real signature? Well, there's a key in the domain above it, which you can use to verify the signature. And then there's a key in the one above that used to verify the signature of the key and the key above that, and all the way up to the root. So by doing multiple comparisons, public key encryption processes, you can verify that everything is properly signed all the way to the top. And the root of DNS you have to just trust. Just like you have to trust the certificate authorities in HTTPS, there is nobody above them to say they're okay, and that trust, of course, turns out to be a weakness when the certificate authorities lie, and that has happened several times, although it's not very common, but it does happen. And when it does, the entire trust model is shot. If the root of DNS was to lie or be hacked or subverted, that would foul this up, and as far as I know, that has never happened. But it could, in principle, happen. Nobody has any solution to this. Every trust model involves having somebody you take as the ultimate repository of trust. And if they lie to you, it all falls apart, and nobody has thought of any other way to do it. The only thing close was the PGP thing where you get all your friends to go to parties and sign each other's keys, and you trust a friend of a friend. So there's not one single point of trust, but there's a sort of democratic ideal that if 5 of my friends say something, that must make it true, which is a different concept of your ultimate trust. But anyway, there is something you trust, which if it's wrong, causes the whole thing to collapse. So in order to make DNSSEC work, the root had to be signed, and that only happened in 2010. So it's only been 8 years that there's been any attempt to seriously deploy DNSSEC. And so you can see it if you just do these queries. If you send a dig to get the resource record signatures of the root, you'll get these signatures. There's a couple of resource record signature records up there. And if you go to get the DNSKEY, you can get DNSKEY records from the server, and you can then do this at all the levels and get them come up, and you'll see these long cryptographic things, which can in principle be verified. And then you can go to the top-level-domain.org, and you can dig the DS signature, DNSKEY here, and the resource record signature. All those things are there, available for your DNS servers or even your client browser to verify this. You can put an extension in your client browser and actually verify these things. And therefore, for a very small number of websites, you can actually be confident you're looking at the right page through DNS instead of HTTPS, but almost none of them are signed. So if you were to block everything that's not signed, you couldn't surf the web anymore practically. So it is still early. And what's pretty discouraging is the root was only signed in 2010. In 2013, you had 332 top-level domains, 359, 1306, 1400. Well, maybe that's all the top-level domains. That might be why it stopped going. But I think it's not. I think the problem is people just lost interest. And a lot of people have written about this. Here's an article I found earlier today talking about this, why DNSSEC deployment remains so low, about a year-old article. And the next slide has the details, which are really discouraging. 37 million domains at GoDaddy, 8 signed. 8,000 signed, none at Alibaba, none at 1&1. Amazon has none. Google has only 2,000 out of 800,000. This is appalling. You know, we're at something like less than 1% of the sites are signed at all. So DNSSEC is completely failing. And people are beginning to just say that. DNSSEC is dead, stick a fork in it, just forget it. It was an idea long ago. And basically, I think everyone has given up. And I think what's going to replace it is a DOH, D-O-H, domain DNS over HTTPS, which seems so much better. We already have HTTPS everywhere with certificates and everything. We could just run DNS over HTTPS instead of bothering to have another set of private keys you're deploying up there. And The only thing wrong with it is it's completely illogical. This is why the guy that wrote Bind was madder than anything. When they officially approved Doe, like last week, and he said, you're out of your mind. Let's think about this. You boot up your machine. First, it gets a MAC address from the hardware. Then it gets an IP address from your DHCP server. Now you try to go to a website. It doesn't even have any DNS information at all. It has to get DNS information. It can't possibly use HTTPS until much later because that's at layer 7. So you have to use unsecured DNS to find the HTTPS server. So what the hell? So from a fundamental logical mathematical sense, this makes no sense at all. But in practice, it works fine because you go to the insecure DNS server, you get your insecure resolution that might be wrong. Then you go to the server trying to set up HTTPS, you check the certificate. The certificate means it's right. So then I can send further DNS resolutions over to your HTTPS protocol. So what it means is I started up using the old insecure method, and the first few queries are not protected. But after that, I can use the secure queries. So in practice, it's okay. It's not mathematically perfect. I think the same thing is true of VPN providers, right? If you want to use a VPN on your cell phone and encrypt all your traffic, you have to find the server at the other end of the VPN. You have to do DNS to find that. So your first DNS has to be unprotected by VPN. This is just, that's not the end of the world. It just means that your privacy is protected 99% of the time instead of 100%. And most people regard that as an improvement. But you know, the purists say, we had a much better system, DNSSEC would fix it. He said, yeah, well, it's too much bother. We'll settle for a thing that's almost as good and a whole lot cheaper. That's the American way. And I have to agree with it. I've mentioned in the other class, Ethernet is like this. Token ring was logical and didn't have any collisions and would always go 4 megabit per second. Token ring would really move data at 4 megabits per second. Ethernet is a mess. Everybody talks at once. The packets collide. You have to resend them. You can, if you have a 100 megabit per second Ethernet network, you can only move about 10 or 20% of the speed before the collisions get so bad that it doesn't go anywhere. So it's like a 2x4. It's not 2 inches by 4 inches. It's 1.5 inches by 3.5 inches. And your 100 megabit per second Ethernet network only delivers data at about 10 megabits per second in practice. But the end result is, even though it is sloppy and inefficient, it's cheaper and faster than token ring because all the effort of making it smooth costs too much. Yeah.
So with Doe, if you were like DNS poisoned and sent to a bad domain, it was, you know, it wouldn't be able to go there. Your browser would see that it's bad because it's got a bad certificate.
You mean if you've got a bad DNS record and it couldn't find the HTTPS server?
Well, yeah, no, if you got a bad DNS record, right, and then it sent you to an attacker's domain, they wouldn't, like your browser would detect that was bad because of the HTTPS server?
Yes, because that if I, for example, am using Cloudflare or Google as my HTTPS or DNS, my Doe server, then I have to make an HTTPS connection there, and then I do DNS over that. And in order to make the HTTPS connection, I have to do a TCP handshake and then get a certificate and then verify with the certificate authority. So if a hacker tries to pretend to be Google, I will accept them and make the TCP connection, but the HTTPS connection will fail. And a box will warn up saying this is not signed by certificate or valid authority, you can't trust it. And then my attempt to resolve DNS over HTTPS will also fail. So I guess my browser will, my machine will probably either refuse to connect at all or go down to the old insecure DNS.
Okay. But you could still man the middle of that and everything because it protected the actual domain name you're going to. So.
Well, it does in the following sense. I mean, once you have established an HTTPS connection, then even if someone man in the middle you, everything's encrypted with a key they don't have. So all your domain names and everything are being sent and returned in a way that they can't be altered or infected.
So it's just your first request now?
It's just your first requests. That's correct. It could be just your first request. Of course, I wonder what it really is in practice. I know most VPNs, 80% of VPNs don't protect DNS at all. They only protect the TCP traffic, and the DNS continues to be done unsecurely. That's a common flaw with VPNs. So I don't know if you turn on a normal HTTPS client, if it really makes 100% of your DNS done over HTTPS or not. It would be a thing to test.
That means that if your first request was sent to a bad server that had a legit certificate, that you could still potentially hack that.
It does mean that. That's a very good, and that's what people are afraid of happened 3 days ago. China hacked Google. They sent Border Gateway Patrol output, or someone did. Someone else is taking the blame. Other people say it's covering for China. But anyway, for some reason, for an hour, traffic to Google went through China day before yesterday. This has happened very often. Several times a year this happens, and is generally regarded as a Chinese military doing this, but no one really knows. But anyway, they man in the middle over the whole world. So traffic going to Google went through China on the way there. So they were in the middle and they could inspect it. Now the question is, what good would that do them? Because everything at Google is HTTPS. And what it means is the people who are using Chrome, which is the most popular browser, would be essentially safe here because Chrome will not allow you to sign Google's HTTPS certificate from another registrar. It knows who should be signing it, and if the government of China, which is a trusted registrar, tries to sign Google, Chrome will not allow it. Other browsers, however, will allow it, like Internet Explorer. So what it means is China would be able to read the Gmail and other traffic from people who are not using Chrome, which is probably like a third of the users, so that might be to their benefit. And I must say, it seems to me like government and military people, 90% of them use Internet Explorer and Windows. They really love it. That's where it mostly is. So they probably can get their high-value traffic because those people don't use Chrome, but I don't really know. Anyway, that's an issue, and that's the point. If you were able to make a valid HTTPS certificate that would fool the browser, then you could man in the middle and get in, and that would be right.
Would that break TLS for HTTPS as well?
It would, because what it would do is fool TLS because the original specification, this is a huge problem with TLS. The whole point of this is why Moxie and Spike and a lot of other people started getting really upset about HTTPS about 10 years ago. They said, you're totally trusting this list of 100 certificate authorities, and a bunch of people on that list are eminently not worthy of trust, like the government of China, and yet they have to be on there because if you took them off, you couldn't resolve any Chinese websites, and that's outrageous. So we really need another test here besides just are they on the list. There ought to be a test, are they on the list, and then some kind of sanity test. What is their reputation? Are they being used to sign something that is outside their geographical boundaries? You ought to have some other dimension of trust here. And that's what Chrome put in, and it's gradually, we're developing that. But many browsers don't have it yet. And that's the problem. And of course, the other thing is you could run an American website and you could decide to buy your HTTPS certificates from China. That's legal. And if you did, you'd have an American website signed by China that should be. And why should your browser assume you didn't do that? Why is that impossible? And it's an issue, So what Chrome does is it just has been a list of the top 1,000 websites and who should be signing them, and it warns you if that's valid, if that's violated, and that's an approximate solution, sort of like this DNS or HTTPS. It is a strange ad hoc solution that does not really cover 100% of the traffic, but it does mean that a large portion of the risk is removed. And this is where the purists get upset, and the pragmatic people say, "Well, I'd rather have half a cup than nothing," and accept this stuff. A lot of people hate Cloudflare. Cloudflare offers HTTPS. My website is HTTPS at Cloudflare, which means I'm running a port 80 Apache web server with no encryption. The traffic goes unencrypted to Cloudflare servers, which then hand a certificate and hand it up over HTTPS. So when you use HTTPS to connect to my domain, it is not encrypted all the way to my server. It's encrypted only to Cloudflare, and then from Cloudflare to my server, it's not encrypted. This is a lot of people got very angry when Cloudflare offered this service, saying, "You bums are degrading HTTPS. It's not really 100% all the way encrypted. You've made some cheap imitation DNS that is inferior to the real thing." And I said, "Yeah, that's exactly what they did, and it's free. That's why I have it. I am perfectly happy to get the cheap imitation at a lower price. But I do understand that it's not as perfect as the other system, which encrypts all the way there, which means I'd have to take care of the certificate and updating certificate and all that hassle, which I'd rather not bother. And it will protect my students from most of the risk. And it does help me evade the stupid college intrusion detection system that detects most of my homework as attacks and tries to block my website for being full of malware. So just using cheap, shoddy HTTPS is enough to fool the college systems into not blocking my projects, and that gets my job done. But I am aware that I am very far from mathematical purity here. Just like DNS over HTTPS is sort of insane and contradictory and not perfect, but it will make people a lot safer. So anyway, Cloudflare is trying to help you get DNSSEC, yeah.
Well, maybe it's over here. Is there any way you can Cloudflare to your server?
Oh, you can, I could. That's a very good point. I could encrypt from Cloudflare to my server. There are various ways. I could put an HTTPS certificate and just let Cloudflare make a connection. I could set up a VPN to Cloudflare. There are various ways to do that, and Cloudflare has blogs about how to do it. So it can be done. And one group of people that has to do that is banks. This is one, my student worked at Cloudflare, and one of his first jobs was to make Cloudflare PCI compliant, which took him about a year. He made it, and the point was Cloudflare was going to be a content distributor for banks. And this means they have to handle real HTTPS traffic to servers that are really using HTTPS, and they have to change their certificate in the middle so they can inspect and block the attacks. And they found a way to do that by mixing several cryptography techniques available. So there's sort of a VPN from them to the bank, and then an HTTPS to you, and they can get their certificate from the bank and pass it on to you without ever holding it, so they don't have the private key. But your traffic doesn't, they had to work out this system, which was quite sophisticated. They have very sharp people, and they solved this problem because it's illegal for them to have the private key, and yet they really want end-to-end encryption, and so they managed to patch together 2 or 3 different kinds of encrypted tunnels to make it work. And that's a good thing, at least in my opinion. Other people are still yelling and screaming about it. There's a lot of people that are purists. For example, there's Steve Gibson, who made the spin right tool to fix your hard drive. He's been around forever. He hates HTTPS entirely. He says, this is evil, this is wrong, this means you're owned by the corporate overlords, you have to pay money for a website, you have to get a certificate from somebody you don't control, this is evil, wrong, nobody should use HTTPS, it's all just a scam. And Kaspersky Antivirus. A few years ago, I loaded Kaspersky, I was testing antivirus products, and Kaspersky got its update over HTTP. And I said, holy crap, I was actually writing a blog post, Kaspersky uses insecure update. And I said, wait a minute. Before I publish this, let me think about this. It seems very unlikely that Kaspersky, I said, before I publish it, I'm going to do a man-in-the-middle attack and alter the update and prove that it takes an altered update, and it didn't. I said, okay, what happened? I went and searched, and Kaspersky has a white paper of their system, which they have reinvented an alternative to HTTPS. With public key encryptions and certificates and everything, they made their own equivalent of a certificate authority, and they have their own complicated protocol, which is adding all the security that HTTPS would have added. I don't know why they didn't just use HTTPS, but they basically invented their own system that does the same thing. So even though it's HTTP and you can man in the middle it, you can't modify the traffic and have it fooled into putting junk in the update in the server. So, you know, it ends up working all right. And maybe that's because they don't want to trust like an American provider to make the server, or maybe they don't trust anybody, they want to run their own. But anyway, they do have some system which, from my cursory test, does seem to solve the problem. And there's also a European community. I used to have a subscription to one of these. There were alternatives to HTTPS in the early days when HTTPS was invented, and there were some European websites that still use the other kind of security, and you have to add a special browser extension and stuff to use it. There are alternatives out there, but most people, HTTPS won the race, and everybody else is of no importance. Anyway, so you can put this extension on, and then you can get a little padlock, and it'll tell you if your site is signed by DNSSEC, which almost nothing is, but you can see it here if you care. Then there's another one here. This is another idea which I think people have pretty much given up on. Dane, you can use DNSSEC as the root of trust, and it can validate your SSL certificates. Now, this is what you might do if you really trust the root of DNS, which, like I say, the root of DNS has never been hacked as far as I know. And the root of DNS is secured by Dan Kaminsky personally and 7 other people. They chose 7 famous people who are widely trusted to sign the root. And they have a ceremony every year where they meet and they bring in their thumb drives and floppy drives or whatever, and they each have like 1/8 of the key. And they put the key together and verify that nobody has altered the key, and they bless it for another year. We have validated you can trust the root of DNS for another year. That is the real system. And that has worked every year. And this is because the general community would rather trust that than like a corporation or a government. They trust these celebrities to vouch for it. And so if you were to bribe like more than half of those celebrities to lie, I guess we could pervert the root of DNS. But if you like that system, then you can use this to sign HTTPS, and that's what Dane is. And you know, it is kind of nuts, but this begs the question, this whole idea that you like to trust people, and the mathematicians get in, they say, well, we could do this math, and you could be 100% sure that you can trust people, but the problem with math is, all math does is take you from your assumptions to the deduction. But you have to start with something you trust. And what can you really trust? And the answer is probably nothing. So it's just a question of your religion. What is the thing that you imagine, oh, they would never betray me? And these guys think that these individual, highly trusted people would never betray them. Other people think, in America, we think anybody rich won't betray you. They worship them because they're rich. So the fact that these are big corporations means they'll trust them. Other people trust their government or their king or something. It's an arbitrary decision. Who do you trust? Anyway, so the protocol is still changing, and of course, it only secures the record to the resolver. It does not protect the traffic from the resolver to the client. It may someday, when it's actually deployed to 99%, we can afford to have a client that will actually not let you go to sites that haven't been signed, but at the moment, almost nothing is signed, so it's not protecting you at all. So This is a game. Anyway, so one option is to force everyone to use your local resolver so that the local resolution happens on your local, more or less trusted network and not going off to the internet. That's one possible response. There's another big issue with this, which is authenticated denial of existence. And this is closely related to the Kaminsky attack we talked about. If you go look for a server and the server is not there, no server can tell you it's not there except the SOA. Other servers have cached records of the servers that are there, but if it's not in the cache, that doesn't prove it doesn't exist. So the only way to decide that fred.ccsf.edu is not there is to go straight to the server. And this turns out to be a problem because people didn't want to make it easy to enumerate all your DNS names. So they have various techniques of using a hash and putting the hash in some kind of order so they can verify that this thing is not there without making it so you can just see every name easily and easily just go through the alphabet and find every name. So there's a bunch of these next, NSEC and NSEC3, multiple completely incompatible systems of resolving this issue, more and more complicated. Anyway. Then there's transaction signatures used by DNSSEC to cryptographically sign messages with an authentication code and a key and a time-based key which will expire and a time fudge factor to deal with the fact that the clocks might not be synchronized at both ends. And you have to generate a secret key and securely transmit it to the other server. It's all kind of madness. And then you got another one, which was told is written with MD5 only, and then there were other ones. There were just these complicated things. And all this cryptographic work means that you can DOS the server by forcing it to do a bunch of mathematics by sending it a request that forces it to do a bunch of math every time it gets it. There's another one, SIG0 for transaction signatures, and another one called TKEY using Diffie-Hellman, and just many, many complicated cryptographic routines, all to achieve DNSSEC, which solves a problem that doesn't matter anyway, which is why, you know, people have pretty much given up. Anyway, most servers using Bytes, some are using an SD. And you can have master slaves, where you have the master data up here and it copies to the slaves. That's what many people do. That's the usual way you deploy DNS. And you can specify that your server is a slave in bind, type slave. So it will not, it will get all its data through zone transfers from the master, and that's what you usually do just to get a load balance there. That's the way domain controllers used to work in the original Windows NT. You'd have a master domain controller and a backup domain controller that copied from it. After that, they all became equal. So every one of them can change something that will propagate to the others. Anyway, you're limited to 512 bytes in a legacy system because DNS requests can only have that much. And that means failover by NS records is slow because it has to send all the data 512 bytes at a time. Sort of like regenerating a failed disk in a RAID array. You're going to be slow while it's doing that regeneration process. When I tried it in 2015, City College had 4 name server records. I think we have a different bunch now, but anyway. We keep messing with it. Another alternative is automatic failover with a load balancer. So you appear to be a single server, but in fact, there are many servers. I found various examples of this before in trying it, where you query a server and you get a different TTL each time you query, even though from the same IP address. That means I'm actually seeing different copies of data behind there. All right. So if you want to protect your service, of course, you harden the system, update the patches, turn off the unnecessary services. When you firewall, they'll only let the traffic you need through, which is typically 53 UDP and TCP. Block your management ports for your whatever firewall, whatever services, and limit things with an access control list. If you have a public resolver, then there's a best current practice 38, I think, that says if you run something like 8.8.8.8 DNS is Google's public resolver, then you should be aware that people are going to use you for denial of service attacks by bouncing traffic off your server, and you should prevent that with rate limiting. So no one can ask the same question more than 10 times per second or something like that. That would help prevent you being used as a vehicle for attacks. So there are scrubbers out there that will block packets that meet DDoS criteria. You can make your own scrubbers by putting Nginx on a cloud server, and there are other people that do it. Most ISPs do this when they are under attack. Cloudflare does it all the time. They have simple tests to remove traffic that's obviously attack traffic. This is commonly done.
What's the difference between that and honeypot?
That's a very good question. A honeypot is a target that someone will attack that's full of fake data to waste their time. A scrubber is like a firewall. It just removes bad traffic. It doesn't lie to the attacker. So anyway, so here's normal networking. So the customer's here, people are sending in traffic, then people sending in traffic, and it still goes through the router and still goes to the customer site and hurts it. So when you put in a scrubber, you detect that you're under attack. So now you send attacker traffic to these scrubber servers, which try to remove all the bad stuff and only pass the good traffic on. This is essentially what Cloudflare is, a giant measure of scrubbers. From our point of view, your server sits here, and Cloudflare does not pass any attack traffic to the server, just legitimate requests. So they serve as a scrubber and a content distributor, so people get their traffic straight from Cloudflare and don't bother your server any more than necessary. So you get to save on your bandwidth costs, and you don't have to deal with the attacks. All right, and so you can monitor your traffic. You should have automatic monitors. There are many services that do this. It got so easy. I even have my own now. I've had none of it. I now have an uptime page here. So somebody put in a device-free service that will tell me my uptime, and there we are. One of my servers went down. I didn't pay any attention. It went down a couple days ago. Guess I'll have to check that out. These are the servers that are attacked all the time and vulnerable, so they do go down pretty often. When I find them up, I get frustrated. It means my students aren't trying hard enough. These two should be down a lot. Especially this one, it's really old. Anyway, but the others are up, so you should have some kind of monitors. There's many systems. You can easily install your own servers that will test for this, but there's plenty of cloud services too that will just test to see if your servers are up, and you should configure to send you alerts when your servers go down, and then because it's much better for you to call your boss and say, the server went down and I'm working on it, then for your boss to call you and say, the customers are complaining, what kind of an idiot are you anyway, the servers are down. You want to tell your boss. You don't want your boss telling you. This is what you do. You got to have backups, of course, of maybe the whole OS, maybe just the DNS zone, and your cloud back servers have to have cloud backups too. Mine do, especially those attack servers, because they're getting hacked all the time. I got backups so I can easily bring them back up in the event of students hacking them. And of course, you have to test your backups. I've worked at companies where the backups are not working for a year and nobody notices because they don't test them. And typically the backups job is not important, so they would give it to the guy who was an idiot, who was off getting stoned, smoking pot behind the dumpster at his break. And since he couldn't do anything right, they put him on backups because what harm could that do? And then it turned out he was not actually changing the tapes and not labeling them correctly. And when you needed to get them, they were all messed up. And really, we should have had like a fire drill, we should have had a routine test of the backups to make sure that they're really there. Otherwise, we'll be really sorry when we go for them and they're not there. If your DNS server is down, but others are up, you get slow response, but you get some response. And if you have a failed record for a long time, you should remove the records that point to it so customers don't keep trying to send traffic to the one that's down. That will improve their performance time. And I've got a few Cahoots. And let's see how it's looking. All right. There's that. And that. And that. Well, by the way, for you online people, I'm sorry I was late. I was at a contest and I forgot my power cord, so it may be about 10 minutes late starting. But we won. Anyway, all right. Yeah, but anyway, the people over here knew that I was here, and I probably should have turned on Zoom. But anyway, looks like a significant number of people did figure out the class is happening. So, all right. I'll get the text document up to record the winners. I like the pace. What is that? Not entirely obvious. Perhaps best not to inquire too deeply into what that is. Anyway, I'll wait a few more seconds. All right, 5 more seconds. I guess this is it. Okay. So, which architecture puts authoritative servers in different autonomous systems? That's network distributed. The AS is the Border Gateway Protocol nomenclature for the identifier of your company. So your company is all one object. City College is one object. Our ISP is one object, actually. Sprint is an object. ATD, those are autonomous systems. And putting servers in different ASs causes them to be network distributed, but they might not be geographically distributed. They might actually be in the same town, but they're on different suppliers' networks. So they are not going to go down because one ISP went down. But they would still go down perhaps if one whole city went down because of like a hurricane or something. Anyway. All right, what DNS delegation system does Cloudflare use? It's direct delegation. You make them your authoritative servers. So everybody that wants to get to you has to go to Cloudflare first. That's how it works. That's how it has to work, because they have to be in charge of the DNS records so they can change them quickly to respond to attacks. All right. So which record provides authenticated denial of existence? This seems a little esoteric to me now, but it's just sort of a mathematical purist. It's NSEC3. There are many other systems to solve this kind of obscure situation of how do you prove that something is not there. Seems a little pedantic, but people worry a lot about it. It is a difficult problem. I don't know how important it really is, though. Anyway, so which system removes the need for significant authorities? Okay, that's DANE, means you can trust the people that sign the root and have no certificate authority. And that might appeal, that might seem more trustworthy to some people. It's really a matter of religion. So I got, let's see if I can cause my device to be visible. All right, so I got M.Dot, I know who that is, and Melanson, I know who that is. And Warren, that looks like a real name. Good, so I reckon I can give you people points. And I think that's it. Let's just take a look and see if there's a chat message. Didn't Nigeria take down a Google BGP, Border Gateway Protocol? What I'm talking about that. What somebody did many times was send false Border Gateway Protocol messages to reroute Google's traffic through China. That happened again a couple days ago. That's happened many times. That isn't taking anything down, and that is not a failure of a system anywhere. What it is, unfortunately, is the weakness of the system that has been there. Mudge talked to Congress about 30 years about it. They said, we're trusting the internet, but the internet relies on BGP, and BGP is totally unencrypted and unauthenticated, and anybody can mess with it at any time. And this is crazy, and it is still just as crazy as it was then. There have been talk about developing something called BGP-SEC, but it's even behind DNSSEC in development. It's not even designed yet, so there's no hope of anybody fixing this problem anytime soon. It is very strange. But it's absolutely true that the large-scale routing of the internet is fantastically insecure. And anybody can reroute at any time, and it doesn't mean anything's broken. That is operating as intended. It would be a lot more sensible if every ISP only had the right to reroute traffic going to them. And there was some kind of master list to look them up on, but there is nothing like that yet. There are very beginning ideas of that, but no serious proposals have gained any traction at all in altering BGP. Anyway, let's take a look and see if there's anything I should say about the projects. Let me bring it up here. Now I see another chat message. I'll take a look there. I think so. There's just some logging here. You can do the Kaminsky attack here if you can get an old Server 2008 machine, although I heard somebody, like Chance told me it didn't work on the one I handed out, although it used to. But anyway, you do have DNS erased TTBS. This is the DOE stuff, which I highly recommend. This, I think, is the real future, DNS erased TTBS. And I should mention Cloudflare now offers this with their 1.1.1.1 resolver. Google offers it of 8.8.8.8. You can resolve your DNS erased TTBS, and I think that would actually benefit the security of most people, even though it is not mathematically pure, whereas DNSSEC seems to have come and gone without doing any good for anybody. That, I think, DOE is in fact going to become the standard very soon. Everyone's going to be doing it. That seems like a very good answer to a real problem. I don't see quiz 6 on Canvas. Yeah, maybe I'm not planning to have a quiz 6. Let's see. Looks like I did plan to have a quiz 6. Okay, I'll look into that. It may mean I miscalculated the final grades. I will post a note on Canvas when I resolve that. Thank you for telling me. It does look like at some point I intended to have a quiz on 6. I'm thinking maybe I won't. I'm going to look at this lecture. It might not be worth talking anymore about DNSSEC. I have a feeling DNSSEC doesn't really matter and it's not really worth going through. I'll mend this page and Canvas. I'm thinking I'll probably just remove it entirely and stick with 5 quizzes. Yeah.
I think there is another project where you can stuff on that. But it requires a previous project.
This thing here?
Yeah. I think it requires like 8 to do 9.
Requires 8 to do 9.
Or something like that. Oh no, it requires 9 to do 10.
Oh, it does require 9 to do 10. Yes, you do need to have a DNS server in 2008. That's right. You have to do 9 to do 10. That's all. But that old 2008 whiz vulnerable to Kaminsky attack, so you can see it. I just moved it to extra credit, and I'm probably just going to remove it entirely in the future because it's a 10-year-old attack. It isn't that important anymore. It was pretty cool. Made Dan Kaminsky fantastically famous for a good reason. It was bloody awesome. But, you know, it didn't lead to a wave of future things based on it. It was a problem. It got fixed. It's over. You know, not really worth studying in great detail anymore. Sort of like WEP. I used to have my hacking shaken into WEP networks, and that's cool, but everybody figured that out and quit using them. So, you know, it's not important anymore. Yeah. Okay. Well, anyway, I guess I'll stop this and let's see what the other chat messages are. Are extra credit projects are more valuable than others? Well, that's a good question. Like I say, the main one is I would do Cloudflare. Cloudflare is really important. And I would do DNS for HTTPS. I think those are the most important ones. DNS crypt is another one of these half-baked ideas that really didn't get anywhere. DNS curve is another one. I think DNS crypt and DNS curve have both been replaced by DNS over HTTPS. That's the one that really won. And I think DNSSEC has pretty much just been abandoned and people are just going to do without it. So I think the most important one here is DNS over HTTPS. And I would check out Cloudflare. Cloudflare is real and remains important. The rest of these things are kind of, these are authoritative servers are interesting too if you want to set them up as a server. That's meaningful. I think I'll put a note here, like an asterisk or something, marking the ones that I think are probably not really worth doing. Maybe make a second check, and these are of historical interest only, which I think is true about half of these. DNS crypt, the Kaminsky attack. 5, yeah, authoritative server is good. Authoritative server will stay as valuable because authoritative servers are important to set up your own servers. That's meaningful. That's not become obsolete. What's that? Linux and Windows, either way. These 4 and 5 are not bad. 4 and 5 are the things you would have to do if you're running a ISP or setting up your own server farm, which is not that common anymore, but it's not obsolete. But I think I would say these 2 are essentially obsolete. And anyway, so I'd recommend 6 and 8 are the most important extra credit projects. And 3 and 4 are not bad either. I think 3 is also kind of obsolete, really. It's just sort of, it was to stop the Kaminsky attack. And it's interesting, but it's built into everything by default, not all that exciting anymore. So if I get a chance, I'll sort these out. I guess I got a couple issues. But I think what I'm going to do is I'm just going to cancel quiz 6 and probably the lecture next time too. I'll have some other topic to talk about, I think. I'm going to greatly abbreviate this because I don't think there's any reason for you to learn a whole chapter of DNSSEC anymore. Last time I taught this, we thought we were going to really deploy it. Now I think we've all pretty much given up and we're not going to deploy it. So it's not worth going into any more detail than we have with DNSSEC. So I'll modify the page to reflect that. Any other questions?
I mean, you can still do the projects.
Oh, sure, you can do. I'll leave them there. You can do them and they're worth points, but I'm going to mark that they're really used to historical purpose. Not really that practical for modern days. Okay, so I'm going to stop the share and I'll go to the lab and help anybody that wants help and put on these updates. All right.